Hi, this is Chris with Sanderson Test Prep, and in this video we're going to talk a little bit about bond type. So when we're talking about chemical bonds, we have a couple common types that we'll see, which include covalent and ionic bonds, and we'll talk about the differences between covalent and ionic bonds. So two key words that we'll see here. When dealing with covalent bonds, we want to think of sharing, and for ionic bonds, we want to think of transfer. Okay, so what are we talking about the sharing of or the transfer of? So we're talking about the sharing of electrons or the transfer of electrons. And why would it make more sense for a particular element in certain bonding situations to share electrons versus transfer electrons? So a lot of this comes down to how close a particular element is in its valence shell to having a full outer shell. And the difference in electronegativity, which is a really important word to keep in mind, I'm going to put it here in red, all caps, electronegativity. So it's a really important word to keep in mind as it relates to differentiating between covalent and ionic bonds. So when we're looking at electronegativity, we want to think, okay, what is that difference in electronegativity between these two elements that are involved in a bond, or these two atoms that are involved in a bond? So a good analogy for that is think about if you're sharing a meal with someone, or even just an appetizer. If you and a friend go to a restaurant and you order some fries and you're going to share those fries. Depending how hungry you are or how much you like fries, you might share them perfectly equally, right? If there are 100 fries on the plate, you might each have 50. But depending on the day, someone might be hungrier than the other person, or someone might enjoy French fries more than the other person. And so somebody might have 60 of those fries while the other has 40. Somebody might have 70 of those fries while the other has 30. And so depending on how that scale balances or how uneven that scale is can determine whether or not you give up midway through, and instead of leaving the plate in the middle and reaching over and sharing equally, you just say, hey, you know what? It looks like you want way more of these fries than I do. You're pulling on the fries a lot harder than I am, so much so that it makes better sense for us to just slide that plate of fries over to your side of the table. And that's exactly what happens in an ionic bond. So if you think of an electron being shared, you have atom number 1 here and atom number 2 here. And there's an electron, right? Think of this as like a plate of fries. Here, I'll use a little bit of like a yellow maybe to we'll put some fries on this plate. So we got a plate of fries here. And you're deciding which way that plate of fries is going to be pulled. So if it's being pulled a little bit in this direction, maybe they're still sharing. If it's being pulled a little bit in this direction, maybe they're still sharing. But once it gets pulled a lot, you end up fully transferring the electron over to one of the atoms involved in the bond. And the same thing would happen with a plate of fries, where if you're sharing pretty evenly, maybe someone grabs a few more, but the plate can basically hover in the middle of the table. But once somebody starts taking way too many fries, right, you go ahead and you transfer it all the way over to their side of the table. And when you have that full transfer take place, that's what we're talking about when we're talking about ionic bonding. So for bond type, when you think covalent, think sharing electrons. And when you think ionic, think transfer of electrons. Now, as it relates to electronegativity, so here, if we think of this as a periodic trend, so hopefully we've already seen this. If you haven't, check out our other videos on periodic trends. But when you have electronegativity, where is electronegativity in the periodic table? Where is it going to increase or decrease? So hopefully if we know our periodic trends, we know that electronegativity is going to increase as we go up and as we go to the right. So when you go in those directions, you are going to have an increase in electronegativity. And let's talk about what that means in terms of the number of valence electrons. So if you're looking over here on the right side of the periodic table, so here we'll look at, like our halogens and noble gases. They've got 7 or 8 valence electrons, right? So they're really close to or even full in that outer shell. So when it comes to like thinking about how much they want to hang on to their electrons, generally speaking, they really want to hang on to those electrons, especially, right, your halogens. So your halogens, they not only want to hang on to their own, but they want to pull on someone else's. Your noble gases are a little bit different because they already have a full shell. They're not quite as reactive, but those halogens there, group 7, they want to hang on to what they have, and they desperately want one more electron. They're so close to that outer shell. So your halogens in a bond are going to pull very strongly on those electrons. And then if we look, instead of 7 valence electrons, where we're 1 away from a full outer shell of 8, what if we look at group 1, where we have a lot of elements that have just 1 valence electron? So something like sodium, for example, and a common compound that we see, sodium chloride. So if we have those two, chlorine has a valence of 7, sodium has a valence of 1. So to get a full outer shell for sodium, sodium would have to gain 7 more electrons. Chlorine only needs 1 electron. So for sodium kind of either has to gain 7 or just lose 1. And what do we think is easier for sodium to do? What's the easiest path to having that full outer shell? So hopefully some of us might have said, oh, well, it might be a little easier for them to just lose the 1 electron than to gain the 7. And then for chlorine, it's the opposite conversation. They would either have to lose 7 or they would have to gain 1. And what's easier to do, to lose 7 or gain 1? For chlorine, it's going to be a lot easier to gain 1. And so that's the perfect match for an ionic bond when we have an actual transfer of electrons. It makes good sense in terms of energy and stability for sodium to go ahead and donate its 1 valence electron to that chlorine. They don't have to share it. Instead of you share your 7 with me and I'll share my 1 with you, sharing doesn't make sense when it's that uneven. When it's that uneven, you say, hey, you know what? Here, you can have this. Chlorine says, thank you so much. And so this is going to be a good example of an ionic bond between those two. Now let's take a look at where on the periodic table we might expect to form some covalent bonds. So if we think of some different elements here, let's look over on this right side of the periodic table where we have a bunch of nonmetals. So this general area over here, this is where we want to think to ourselves, here we're looking at some covalent situations, some sharing situations. Because we have elements that are going to be much closer in electronegativity, one element is not going to rip the electron away from another, but we're going to have elements that share electrons to achieve a full outer shell. So something like carbon dioxide. So if we have CO2, oxygen has 6 valence electrons, so it needs 2 more. So each one of those oxygens could bind to the carbon, and this is what it would look like. And we'll talk about Lewis dot structures in order to draw that out in a later video. But this is what it looks like visually. But basically what's happening here is oxygen and carbon, nobody's stealing anyone's electrons because they're very close in electronegativity. So instead of pulling the electrons and actually transferring the electrons from one atom to another, in this case they're sharing them. Carbon says, okay, well, I've got 4. Oxygen says, I have 6. Can I share 2 of yours? And you can share 2 of mine. And the other oxygen says, hey, I'd like to share 2 of yours also. And together, those 2 oxygens give that carbon those 4 electrons that it needs to share to have a full outer shell of 8. The carbon gives each oxygen 2 electrons that it can share so that it has a full outer shell of 8, everybody's happy. So because we have closer values of electronegativity, we're able to observe a sharing of electrons rather than a transfer of electrons. So remember, when talking about bond type, you're going to see covalent sharing and ionic transferring of electrons. And to understand when you're likely to see each, it has to do with how close these elements are in terms of their electronegativities. And a really good way to look at it is if you have elements that are over here together on the right side of the periodic table, in that section of nonmetals there particularly, that's where you see the most common examples of covalent bonding. If you have an element like we saw previously, where you have something from the left side with something from the far right side, that's usually what we see when we're dealing with ionic bonding and a difference of electronegativity that is strong enough where we have a transfer of electrons. For more, please check out our other videos, and thanks.